Okay, so this is a little different for me. We'll see if we like it. We need to take a look at what's going to be on your Unit 3 exam coming up. One of the things I can do about this with this is, let's see if I can do it. I can expand. Ooh, makes you dizzy. So we'll break it up into different parts. The first part is about the Earth, the Sun, and how the Earth happens. So I've got your review sheet here. Let's see, one of the things you need to know is the Earth. I'm looking at your review sheet. Plane of the ecliptic is one of the things. So if I ask you what the plane of the ecliptic is, you kind of say it's this thing right here, the sheet of paper that the Earth and the other planets come and orbit the Sun, the plane of the ecliptic. Let's see what else. Again, I'm kind of looking back and forth here. One of the things, and I don't know how it's going to be asked, but I want you to know that the Earth's axis of rotation is tilted 23.5 degrees. And if anybody asks, actually, that is what gives us our seasons. And I'm going to kind of remind you of how that works. I notice on your sheet, there's a question of this. The northern axis of rotation is pointed to the star Polaris. So... okay. Oh, I'm going to ask you questions about these 5 important lines of latitude. Of course, the equator is the equator, it's 0 latitude. And then we have 2 in the north and 2 in the southern hemisphere. And they're both at 23.5 and 66.5 or 66 1/3. I've heard it both ways. So we have our tropics at 23.5. Tropic of Cancer is north. Tropic of Capricorn is south. And at 66.5 or 66 1/3, we have our circles. We have the Arctic Circle north and the Antarctic Circle in the south. So kind of know those. Yes. And then I have generally know when the equinoxes and solstices happen. Looks like I don't have the whole slide here. But know that you're looking at, 3 months apart. So we have our winter solstice and our summer solstice 6 months apart. So in December and June, and if you go anywhere between 21st, 23rd, that would do it. Now the significance I also have on my sheet, know that, for instance, during the winter solstice, if you are above the Arctic Circle, you're not going to have any daylight. In the summer solstice, you're going to have 24 hours of daylight. Of course, the southern hemisphere, it's flipped. So I think that's what I mean by know the significance. Probably the significance on the equinoxes, and again, I apologize, it looks like it got chopped off. I don't think I can find it back again, but what I'm missing down here is, let's see, after winter we have spring. So if you want to put spring equinox, you can. It's the same thing as vernal equinox. And then after summer, after summer we have the fall equinox. Okay, so we're looking at, the date got chopped off. This date right here would be what? September? September. And again, if you just simply put 21 through 23rd or so, that would catch it. Now, the importance of the equinox is that, like the slide says, the amount of daylight and nighttime is the same, all latitudes. All right. One of the things I have on the sheet is, if you were to be patient enough and watch the stars throughout the course of a night, what's going to happen is that stars near Polaris are going to go counterclockwise. And they make that kind of bullseye appearance if you leave your shutter open on your camera. So counterclockwise around Polaris. Even though they stay in their constellations, they look like a pie, kind of. And they come to kind of converge in Polaris. I think that's it for that. And then on to part 2. So first on the sheet is, what is the order of the planets? And this probably will be a multiple choice question. So you want to jot down your card if you don't already know the order of the planets. I have a question on here, know a little bit about each planet. And that's a tough one for me. I don't think I included all of the slides for the planets, but you're just going to have to look over them and have each slide. I would jot down what's important. Like, for instance, the great red spot is on the planet Jupiter, okay? This, though, is good. It says a few things. Now, on your exam, I'm going to have a question about Sirius. Sirius actually used to be a regular old asteroid in the asteroid belt, and hopefully you would tell me the asteroid belt is between Mars and Jupiter. And Sirius now is a dwarf planet, just like Pluto. Okay, so I know that's on there, right? So again, I may not show you Great Red Spot is associated with the planet Jupiter. You're just going to have to know that. All right, so the formation of our solar system, it's generally called what we call the condensation theory. And I think on your review sheet I said no major terms. No as in K-N-O-W, not N-O. So our solar system started out as a solar nebula. The particles got larger and the solar nebula flattened out and rotated. Planetismals, which are ultimately going to form planets, were kind of these, I talked about kind of a snowball effect sort of here. That's number 3. Protoplanets came after planetismals. Okay, your snowball's getting a little bit larger there. And then at the about 4.6, or this says 4.5, 4.6 billion years ago, our sun turned on, began nuclear fusion in its core. Okay, so there you go. Hope that works for you. Know some terms and kind of be able to talk you through it. Then I had some names. I have Aristotle, Plato. Look at that, Plato's there. And then I have Ptolemy. Now, Aristotle, Plato, and Ptolemy all thought that actually everything orbited the Earth. That's the sun orbits the Earth, the stars orbit the Earth, and I just think that's amazing to think about like that. So there's Aristotle, Plato, and here is Ptolemy. I'm missing a Y here. Look at my slides, got kind of messed up here. Ptolemy, and this was kind of the last gasp at the Earth-centered or geocentric model of our universe. And remember, Ptolemy had this sort of, he had the planets orbiting the Earth like this. Okay, oops, sorry, that's Earth, not a sun. Planets orbiting the Earth, and then he had them kind of do these like little loop-de-loo motions, okay, around what they call epicenters. And dude, if you need to add all of these crazy little things to your model to have it make sense, then you're getting away from simplicity, which probably means you're getting away from the truth. So Ptolemy thought centric model too. So beginning Copernicus, kind of, I think I've heard it called the Copernicus revolution. He then actually brought up, again, he wasn't the first to think about it, but let's go ahead and put the sun in the middle of our system of planets. And then here you see the Earth, and here you see Mars. Now, I don't have a question about retrograde motion, but this is retrograde motion this semester. Retrograde motion was where the planet appears to go backwards against the background stars to us. All right. So Copernicus was a heliocentric or sun-centered model. After Copernicus, we have Tycho Brahe, which gathered a whole bunch of awesome or good data, solid data, that he then hired Kepler to understand. And here in a minute, we're going to look at Kepler's 3 laws of planetary motion. The big thing that Kepler had to overcome that others before him weren't willing to make the leap is that the planets don't orbit the sun in circles, they orbit the sun in what we call in ovals, what we call ellipses. Let's see, what else do we have? So here's Kepler's 3 laws. His first law is the shape of the orbit of the planets. His second law is that near perihelion, so maybe you're going to want to know the word perihelion. Near perihelion, or when the planet is closest to the sun, it moves fastest. And when it's farthest from the sun at aphelion, it moves slowest. Now, I know that's not like the title of his second law. His second law, says basically the planet will sweep out equal areas, but it does sweep out equal areas. It goes, and these areas are equal. Okay. Kepler's law then said that the closer you are to the sun, like I said in class, I think it's a gravity thing, the closer you are to the sun, then the more quickly you're going to move around the sun in your orbit. Not only is your ellipse going to be smaller, your path's going to be smaller to complete one orbit, but literally you will move more slowly in your orbit. That's Kepler's third law. All right. So the sun, just had like a couple slides on the sun, but you're going to want to know the 3 interior zones, and the middle is the core. That's where nuclear fusion is happening. Fusion, and I think did I have that as a question? Sun producing energy, where and how. So sun producing energy where, it's the core, and how, I would just simply, and I think I might have put this up on the board, H, so hydrogen plus hydrogen goes to form helium and lots of energy. I know I'll put an E for energy. I know it's more complicated than that, but that's kind of what we call nuclear fusion, fusing 2 smaller atoms to make 1 larger atom and releasing energy. So that's the middle of the sun is the core. Then outside the core we have the radiative or radiation zone. Outside the radiative or radiation zone we have the convection or convective zone. Okay. Once you get out to the surface of the sun, you're on what we call the photosphere, and then beyond the photosphere we have the chromosphere, and beyond the chromosphere we have the corona. And I am going to have a question, test isn't quite made out yet, but I am going to have a question about solar wind. So solar wind is amazing, and it's not really shown on here, but solar wind is kind of this positive pressure in all directions from the sun. So solar wind is an ongoing feature. Let's see, what else do we have? Features on the sun. Oh, yeah, don't have a test question, won't have a test question about features, but I will have a test question about this, that in general, in order to understand the 11-year cycle, you need to know in general that the sunspots, and this is a sunspot up here, sometimes the sun is blank, and right now the sun is really pretty darn blank. When it's blank, we call that a solar minimum, and I'll kind of draw your attention to this little figure. So this would be solar minimum. This is kind of where we are. If we have lots of sunspots, it would be up here. And so this is what we call a max. So from max to max, okay, you're looking at, in general, 11 years. And from min to min, you're looking at 11-year cycle. See what else we got. So I mentioned that I'm not going to have all the slides of the planets. You need to know the planets in order, the order of the planets. We do have 4 inner or terrestrial or rocky planets, and then we have 4 outer Jovian or gaseous planets. I am going to have a question, I think, on there about, with regard to the gaseous planets, what do they have in common? And, well, first off, they're made of gas. If you go to step on them, there's no surface to step on. The other thing is that all of the gaseous planets have bands. Some are more predominant than others. Jupiter's bands are very obvious. The others are not, but they're there. And that all the gaseous or Jovian planets have rings. And Saturn's the planet that rings look most obvious. But Jupiter, Uranus, Neptune also have rings. And all these Jovian planets are, it's like they swallowed a terrestrial planet, so they actually have a rocky core. There is going to be a question on there about AU, an astronomical unit. It's actually kind of one of the shorter distances in astronomy that we talk about, and it's the average distance between our planet and the sun. So that's 1 AU. You'll have a question on there about the 3 M's. So actually they're listed as they occur. So a meteoroid is a space rock. A meteor is fast. It's that streak of light as the rock disintegrates or heats up in our atmosphere, and if anything makes it to the Earth's surface, we call them meteorite, if you can pick it up. So know those. And then just know in general what's up with a meteor shower. So a meteor shower means you see lots of meteors, and the way we see lots of meteors is that the Earth is pushing through, I think we're going this way. The Earth is pushing through debris that was left by a comet. So here's a comet's path, okay, and as the comet gets close to the sun, it breaks up, and it can leave those crumblies there for the Earth to pass through. And actually, in this sort of scenario, the Earth would pass through 2 crumblies that were left by the same comet. Okay, so that's all part 2 of part 2. On to part 3. You need to know about that. Well, I think the reason I pulled this one in is I'm not going to ask you about the formation of the moon, but I am going to ask you about the term regolith. Might be a vocab term, I'm not sure. But when I see this picture, it just screams regolith. It's that powdery stuff that's all over the surface of the moon. Now, the moon basically has no atmosphere. has what we call an exosphere, and also the moon has no wind. So that footprint is there to stay. What did I start to say? So regolith. So basically, and like your book would tell you that, and the slide also tells you that regolith was formed by millions and billions? Millions of years of being pulverized. Billions of years of being pulverized. Then you're going to want to know just kind of general features of an impact crater. So I have some words up there. For instance, I have ejecta blanket. You know, for you budding artists out there, maybe you want to be able to draw a crater. Some craters have those central peaks. This is a good one, the central peak. Some craters have some terracing. I can almost see some kind of terracing there. Okay, so those are features of an impact crater on the moon. I don't think I have it, but I'm going to mention it while it's here. This is a real RILE, and we see these also on the planet Mercury, and they were formed as the planet cooled. Let's see, that might be it. Okay. Yep, I guess before I leave this slide, two important things. So we figured those dark features on the moon actually are called mare, and the light features on the moon are called highlands. Yep, that's on there. Going to be on there. Now, the Earth spins on an axis of rotation, and it spins on its axis and orbits the Earth in the same amount of time. And I can't believe I had this slide, but I didn't say on my slide how long that is. Actually, that's 4 weeks or 28 days. Sorry about that. So it spins on its axis in 4 weeks, and it orbits the Earth in 4 weeks. Okay, so here, if it's 4 weeks, here we see week 1, okay, week 2, week 3, okay, and week 4. So this is what we say is this is the near side. I'll put N for near side, and this is the far side of the moon. Let's see. I think I go on to the next. You are going to have a question or two on there about phases of the moon. Okay, so we have a new moon here, and then we go into a crescent. Specifically, it's a waxing crescent. Then we go into our first quarter. We're still waxing. We have gibbous, and then we go full moon. You can kind of see where it is relative to the sun and the earth and the moon. And then we have a waning process. So then we go into the waning gibbous, and then we go to the last or the third quarter, and then we're still waning. We have a waning crescent. So know those phases. There'll be a question about earthshine. So earthshine is where you can kind of, this is what, a crescent. In fact, we said that this is a waning crescent. You can sort of see the crescent moon, and earthshine's best when the moon is a crescent. And this right here is just a light that's scattered off of the earth right here. And we see this side that's not directly lit by the sun, but it's backlit by the earth, which is lit by the sun. Okay? Let's see. Tides. So know that the thing that gives Earth's tides is actually the presence of the moon. And I think this is good. You can kind of see the moon, wherever the moon is, it's kind of lifting up the oceans. And actually the side opposite of where the oceans are being lifted up, so this is be high tide. Over here it's also high tide. So that's why we have high tide every 12 hours. And then I'm also going to include a question about these especially affected tides. So we have an especially high tide if the sun is in line with the moon. So that will have especially high tides at either new moon or full moon. And then we'll have diminished tides, we call neap tides, when the moon is at a right angle to the sun. So here's the sun over here, moon at the right angle. That will happen is either first quarter or last or third quarter. Remember, last quarter and third quarter mean the same thing. All right, so those eclipses generally know I think it's probably going to be the configuration of the Earth, moon, and sun when we get our eclipses. So down here, this is a new moon. We have potential for a solar eclipse. And over here, this is a full moon, and we have a potential for a lunar eclipse. So know those. And then on to part 4. So let's see what I pick. I didn't pick out a whole lot for part 4. I am going to ask you a question about parallax. And remember, parallax can apply to something that's relatively close as the observer moves from side to side. Now, in class, what we did was we extended our finger, and then we alternated. How'd this go? No, we put our finger not too far from our nose, and we close one eye and close the other eye. We could see the finger move. That's parallax. The farther we move our finger away from us, then the less parallax we see. Okay, so that's parallax. I think on here the big thing is that right now with our current set of constellations, you're looking at 88 constellations that are generally based on Greek and Roman mythology. They're unequal, and that's what our culture has, and other cultures would be different. And then I guess I do have more concept here. It's the concept of the celestial sphere. And a good way to kind of picture of the celestial sphere would be this one, where this ghosty looking thing basically has the stars imprinted on it. Now I know that the stars are not always this, not by far not the same distance from the Earth, but that's why this is just a model. And we can kind of think of then the that celestial sphere spinning around with the Earth in the center. Excuse me. So that's the concept of a celestial sphere, and it kind of gets us down the road a little way. All right. Now, as preparing this, I don't think we have finished. This is kind of where we petered off. We've started talking a little bit about stars. Let's see what I put. Stars, giant molecular cloud. Yep. I kind of want you to know the concept of a giant molecular cloud. And this actually is not a good concept of a giant molecular cloud, because this is just showing you kind of the formation of our solar system. Think of a giant molecular cloud. This is pretty good. This actually is a photograph of the Pleiades, otherwise known as the Seven Sisters. And in a giant molecular cloud, or GMC, basically there's a bunch of gas and dust that a bunch of stars can be formed from. That's a giant molecular cloud. Okay. I have on your review sheet, I say what makes all these stars look so different, and the answer is mass. It's the mass that they start with. So for instance, we talked about the concept of giant molecular cloud, a bunch of stars being born at the same time. Well, some stars are going to have a lot of material, and some stars won't have so much material. So that's kind of what I mean. They're going to have an assortment of masses. So the less massive stars are going to be reddish in color. They're going to live a lot longer and end their lives quietly. The more massive stars will be hotter, and so with hotter color, with being hotter, then they'll be bluish in color. They will live short lives. I know it sounds strange because they have a lot of mass, but they'll run through it faster, and they'll end their lives explosively. Okay. So kind of know that. Let's see, what do we have? We use a brightness scale, and it feels a little backwards. And what I'm going to test you over is what we call the apparent brightness, or the brightness scale. So the apparent brightness, or brightness, actually, how do I say this? The more negative the number, then the brighter it is. And the greater the positive number, the dimmer it is. So it's based upon a +1 being, at the time that Hipparchus developed it, being the brightest star, and +6 being the dimmest. And like I said in class, it is actually, or will say in class, it does vary by a factor of 10. So it's not linear, it's what we say logarithmic. Okay, so I am going to have a question about this HR diagram. We're talking, actually on the next slide I'm going to show you, but when we talk about how stars live their lives, they kind of go through these different stages. So this is called the HR diagram, or Hertzsprung-Russell diagram. On the HR diagram, we can kind of see these different stages. So this is one stage, okay, it's called main sequence. Up here, I'll put a 2, and actually maybe even a 3. It kind of depends upon their mass if they're going to go up here. So they will leave stage 1 and move up here on the HR diagram. Now, you're going to want to be able to maybe draw your own HR diagram. And the way it works is we have the hottest temperature over here along the x-axis on the left, and we have the coolest temperatures here. So I would put that on my HR diagram. And then I would put increasing luminosity. I'll put a big L for luminosity. Increasing luminosity as you go up. So this is to say that these guys over here are relatively cool, okay, but they're relatively bright. That's how that works. And then on the HR diagram, we've got some of my favorite group of stars down here, the white dwarfs. These guys are called white dwarfs, and they're another name for them is retired stars. So be able to, hopefully this will make more sense as we go through it in lecture, be able to draw an HR diagram, kind of the little clusters of different groups of stars on your brain. So related to the HR diagram is simply this. So you can kind of see this is an HR diagram of sorts. So we see here, this is the main sequence. Okay, this is the cooler temperatures, this is the hotter temperatures, this is the increasing, I'll put L for luminosity, increasing energy output. So you can kind of see it leaving the main sequence, and you see it going up here. Now I do have a question, there will be a question about something called planetary nebula. And if you're like, I've heard the nebula before, well, the word nebula we actually brought up when we talked about the formation of our solar system. We called that a solar nebula. All a nebula is it's got dust and gas. And the thing about it, in this case, this planetary nebula, if you kind of follow what I'm saying here, is this actually planetary nebula is given by a star that is aging. It's kind of sloughing off its material. There's some beautiful planetary nebula that we'll see in class, but that's an example of a planetary nebula. Let's see. Now, what do I have here? Well, so here you can kind of see planetary nebula. This says interstellar cloud, but works the same way. A protostar, high mass star, super red giant, and I said that massive stars go out. They're destructive. They blow up into a type of what we call supernova event. Now I am going to ask you about 2 crazy objects. I'm looking at your review sheet. At the bottom of part 5, I say what's with the neutron stars and what's with the black holes. Okay, so I'm going to kind of show you what that looks like. Now, a neutron star is the result, or happens, or is created after a star has blown up. So this is a figure of what a neutron star looks like. Now the thing about a neutron star is basically this is neutron soup. I'll put a little N. You know, we talked about neutrons and protons and electrons. Basically the material that was the center of the star that blew up, it's squished down so much that the protons and the electrons merge to form neutrons, or neutron soup. What you're looking at here, and so I don't know how I'm going to do this. I might use, if you want to put on neutron star, if you want to go ahead and put, where I'm looking for pulsar. If you want to go ahead and jot down a pulsar, that might be the form of the question. Because what happens with this star, with the remnant of this, the leftovers of a blown up star, is that it probably has a lot of spin that it conserved as it was a big star. Now it's a smaller neutron star. So we have this thing spinning, and as this thing spins, basically it kind of sweeps out into outer space a signal that can be picked up by a planet such as ours that's in its way, and the recurring signal we call a pulsar. All right, so we'll see what we do with that. The last thing I want to talk about, and it's something that especially when people take, here's my plug, if you get a chance, go ahead and take an astronomy class that does more than just 4 weeks of astronomy. Sometimes people take an astronomy class to understand what is up with this stuff we call black hole. Well, a black hole, as I said a minute ago, can be the outcome of a star that's blown up. And with a black hole, basically, the matter has squished in on of itself that it doesn't stop with neutron soup. It keeps collapsing and collapsing. And so that's why I kind of say it basically collapses in on itself. Okay, and it's so there, the way that works then, if this is my BH, my black hole, there is a region around a black hole called an event horizon, and I'm not sure what the test question is going to be like regarding a black hole, so you might want to jot down event horizon. And that event horizon is the space beyond the black hole that if you go too close inside the event horizon towards the black hole, you are not going to escape, because even if you had an escape velocity, which is how you get away from gravity, even if you have an escape velocity that was as high as the speed of light, you're still not going to be going fast enough, and you're basically doomed to fall into the black hole. So I'll see what I can come up with. I guess the other thing, maybe I'll do this for black holes. How do we know that there's black holes out there? And what you're looking at here is, this is a normal star. I'll put N for normal. And then this star has a companion, and I'll put BH over here. This is a black hole. And so what's happening is matter from the normal star is kind of, it's like water going down your drain, your bathtub drain or something. It's actually matter's being sucked off this normal star, and it creates what we call an accretion disk, and it creates energy, an energy signature. All right, so on to the last part. And so I've got 3 things here listed on your review sheet. One of the things I might ask you a question or two, or maybe even for, like I said, you budding artists out there might want to be able to draw this, but what is the structure of our galaxy, our Milky Way galaxy? Where our galaxy is a spiral galaxy. I'll go ahead and put it spiral because it's probably coming up later. And it's got 4 major arms, and it's got a nuclear bulge in the center. Our sun is about halfway between the nuclear bulge and the edge. Speaking of how wide it is, or whatever, let's see if I don't have any. Yeah, it's about 100,000 light years from side to side, just like the Monty Python song says. With regard to its thickness, its average thickness is about 20,000 light years. I think that should do it. Another question, and I don't know, like I said, I guess since I'm doing this review session, it's fair game. You might want to put Sagittarius A star on your note card, because actually, as it turns out, here in the center of our black hole, center of our Milky Way galaxy is a black hole, and the black hole actually is in the in the direction of the constellation Sagittarius. So when we talk about Sagittarius A star, we're talking about that black hole in the center of our galaxy. All right, so 3, 4, sometimes 5 types of galaxies, but what I think I'm going to hold you accountable for are the spiral galaxies, like the Milky Way. And this is a spiral, but you can't see it because it's what we call kind of edge on instead of face on. Barred spiral, so it's a spiral, but it's just kind of got a main bar of stars instead of our kind of 4 relatively equal arms. I guess as it turns out, am I thinking of this right? Now we're thinking that our Milky Way galaxy is more of a barred spiral than a spiral. Ellipticals, these would be ellipticals. Ellipticals don't have arms. They're just kind of... they don't have arms. And then the other one is irregulars. And this is, I think this is the Large Magellanic Cloud. Yep. And we can't see that from the northern hemisphere. It is totally on my bucket list, though, to see it in the southern hemisphere. And we're going to talk about some things with regard to our universe unfolding. Kind of what you're looking at here. The structure right here, that actually is our universe. So that's the fabric of our universe. But one of the things Einstein said is that the fabric of our universe, the space of our universe, and the time of our universe, space and time actually is a single entity, which totally blows my mind. But I think, like I said on your review sheet, I want to kind of get a... oops, right. I want to go ahead and get an estimated... age of our universe, And so we're looking at about 3.7 billion years old. Excuse me, 13. Final answer. 13.7 billion years old is about the age of our universe. So I hope that helped. Let me know if you have any follow-up questions.